Okay, so the question we were asked in class for homework 1 part A was explain the momentum, heat, and mass transfer analogy from the perspective that the flux of momentum, heat, and mass are each related to their respective concentration gradients via a diffusivity that has units of meters per squared per second. And as I have here is a little text that I pulled from the textbook that just says, in heat transfer analysis, the ratio of the thermal conductivity to the heat capacity is an important property termed the thermal diffusivity alpha, which has units of meters squared per second. And I just added this to kind of support how we're going to go from fluxes to gradients. And then we're going to use that proportionally with their units in unit conversion to show how we can go from one unit to the next and cancel to get our goal of meters per second squared. Just adding on to that next point, so we're looking at momentum, flux, which just is shear stress that we learned in transport 1. We have heat flux, that's right. Heat flux, which just is heat flux. Add that. And then we also have mass flux, which is the same as mass flux. And what we have is we're trying to get the flux and flux. I should add that before. Let me go over. So flux is going to be, in its simplest terms, it's unit area over unit time, which, as you can see, kind of relates up here to the diffusivity of meters per second squared. So now we're going to start with momentum flux and show how to get to basic units to meters per second squared. Okay, I've just given myself a little outline to remember everything. So starting with shear stress, we have, so shear stress, as I said up here, is just momentum flux. And what we're going to do is find momentum flux in the velocity gradient, and then find the dynamic viscosity by using these two right here as ratios. And that's how we're going to solve all three. But starting with this one, so shear stress is in units of newtons per meter squared, which is just a Pascal. And then the velocity gradient is going to be velocity over length. And the velocity we're going to be using is meters per second, and length is meters. And then these two cancel. So we're left with Pascal seconds. Or sorry, we're left with seconds. I'm getting ahead of myself. So then we're going to do shear stress. So we got, dynamic viscosity, which is shear stress over the velocity gradient. So we're just going to take these two. So we're going to get pascals per second. I found where my mistake was. So since this is a fraction, this should be equal to seconds to the -1. So we're going to have seconds to the -1, which equals a Pascal second. I knew I messed up at this part when I was getting Pascal over second over then Pascal seconds. Okay. So now we're trying to find the momentum diffusivity, which is represented by this V. So we're trying to find that, but first we need to find density. And we can just put density is equal to kilograms per volume, and we'll use meters cubed here. And then, so we'll have V equals, and then we'll put that in the denominator, meters cubed, and then we got to find this U, which we found up here is the dynamic viscosity, so Pascal seconds. And then we have to remember that a Pascal is equal to up here what we put, kilogram meters per second, or meters second squared. So we'll add that. So we get kilogram per meters times second, times seconds over kilogram per meter cubed. So now all we have to do is do some rearranging of the units. Okay, so now when we cancel, one of these kilograms go, well, the kilograms cancel, and then one of these seconds goes away. And so we got to flip, this goes away and this becomes a meter squared. And so we're left with this second and this meter squared, and then you got to flip them because they're on opposite sides of the denominator. So we're left with meters squared per second. And as you can see, our momentum diffusivity is equal to diffusivity up here, which is always in meters per second squared. So that solves the first part of the problem of explaining the momentum transfer analogy. So now we're going to move on to heat. Okay, I got our setup here for the second one. Okay, heat flux going to meters per second squared to show that they go equal in diffusivity. So our units heat flux are going to be watt per meter squared, and our units temperature gradient are going to be Kelvin over meter, I believe. And then we're going to have to do the same ratio that we did before. So we're going to have watt per meter squared over K per meter, or Kelvin per meter. And then when we cancel, we're going to get, let's just write it out. We're going to get a watt per Kelvin meter, I believe. And then as you can see here, I just added this from what I said earlier from the Transport 2 textbook that we're using this semester. We have alpha equals K over rho CP. So I'm just going to rewrite that out because we're going to use it in a second. So we're trying to solve alpha. Alpha here will be the heat diffusivity. And the K is going to be what we just solved. So it's going to be watt per Kelvin meter. Okay, I just wrote some other things down here in this corner that I wasn't too familiar with. So we have joules over kilogram Kelvin, and we have a watt is a joule per second. So going on, we got density, kilogram per meter cubed, and we have joule per kilogram Kelvin. So what's going to cancel here is our kelvins will cancel, and our kilograms are going to cancel. I think that's really it for now. And then we can use this and plug that in. So we'll have alpha is equal to joule per second meter in the numerator. And then we'll have joule per, is that it? Yeah, per meter squared or cubed in the denominator. And then we'll have these joules will cancel, and one of these meters will cancel. Oh, let's not do that. Let's do this. 2 meter canceled, and then since these are both in the denominator, they'll flip. So we'll get meters squared per second, which is what we're trying to find, which is the thermal diffusivity. So that's the second part done, where we're trying to relate heat flux to thermal diffusivity. And we have here momentum flux related to momentum diffusivity. So our last one here will be to do the same thing with mass, which hopefully should be the easiest one. Okay, I just set up our outline for the mass flux. And what we're going to do here is find our mass flux unit, which is given as kilogram per meter squared per second. And then this concentration gradient unit I wasn't too familiar with, so I looked it up and it was kilogram per meters to the fourth. So we're going to do exactly what we've been doing and set up this ratio. So we're going to have kilogram per meter squared seconds and kilogram meters to the fourth. So what we're going to have here is our meters are going to cancel, well, not all of them. Let me go back. Well, this meter will cancel all the way. These kilograms will cancel, and this will be down to a second. So yet again, we're left to seconds per meters squared, and then they're going to flip because they're in the denominator. So what we're left with for the third time is meters squared per second. Okay, so I think that fully answers the question that you wanted the answer to. Explain the momentum, heat, and mass transfer analogy from the perspective that flux, momentum, and heat are each related to their gradients. So let's check. So our momentum flux, we started with our, I'm going to use a highlighter for this part. Actually, I'll use my laser pointer. So we used here, we started with our shear stress, which is just our flux. These are the same thing. Started with our flux and set a ratio with our gradient here and canceled units to find, canceled units to find meters per second squared. So that one's good. Heat flux, took our gradient, set this ratio right here, and then we found this ratio and used it with our density and canceled units to find meters per second squared. And this last one was the easiest one, like I said. And we set our ratio and used our gradient and our flux to find meters per second squared. So looks good. And now let's move on to the second question. Okay, time for the second question. As you might see here, I do already have an outline, and that would be because I recorded for 30 minutes and forgot to screen record. So that would be why not half, but a lot of the stuff's already written down. I just don't want to rewrite it. So the second question is explain Fourier's law, i.e. what are the units of flux, thermal conductivity, and temperature gradient, and why is there a negative sign? What is the difference between thermal conductivity and thermal diffusivity? Okay, we're going to start with the heat flux, the thermal conductivity, and the temperature gradient first. Okay, so in short, a little short summary is that the heat flux here is going to be proportional to the temperature gradient. So that's mainly what Fourier's law is about. But let's go one step at a time. What Q is telling us is how much thermal energy. I'll write this down. Sorry, I'm being so quiet. I gotta focus. Otherwise, I'm gonna forget. Okay, so what our heat flux is just demonstrating is how much thermal energy is flowing through a surface per unit area and per unit time. That's going to be, as I said earlier, proportional with the temperature gradient. Okay, moving on to K, our thermal conductivity, which we're going to talk about later is goes hand in hand with our thermal diffusivity. So the area units for K are going to be watt meters per Kelvin. And what our thermal conductivity kind of is how easily heat flows through a material. So think of something that is like a good conductor, like metal. Like metal is going to have a high thermal conductivity because it is very conductive. And something like insulation is going to be a bad conductor and have a low thermal conductivity because it wants to keep heat in. It tries to stop heat transfer. So yeah, that's thermal conductivity. And then our temperature gradient, this is just Kelvin per meter. The easiest way to explain this is just how the temperature moves related on position. So one side's hot, one side's cold, and your Kelvin's going to be different based on your position. So that's basically our Fourier's law. What are the units of thermal conductivity and temperature gradient, and why is there a negative sign? Okay. Yep. Okay. So I kind of have this from what I messed up earlier. Negative sign, high to low temperature, and it will model real life scenarios. So sorry I already have this written down, but so the negative sign just ensures that the Fourier's law will flow from high to low temperatures, and it will also model real life scenarios. So without the negative sign in the equation, we wouldn't necessarily be able to use the law just because of it not modeling actual scenarios that happen day to day. Okay, and then the last part, let's talk about the difference between thermal conductivity and thermal diffusivity. I kind of already talked about it. We can look at this example. I have to erase all my stuff and redo it. But in heat transfer analysis, the ratio of thermal conductivity to heat capacity is an important property termed the thermal diffusivity alpha, which has units of meters per second, or meters squared per second. So let me erase all my work and then I'll be back. I just erased all my work. So we have this textbook grab that I just read. So let's go walk through it. So we have alpha is equal to K over PCP. And as it says up here, K is the ratio of thermal conductivity to heat capacity, which is this. So really what we have is thermal conductivity over this stuff that doesn't matter, but heat capacity. In short, this alpha here, our thermal diffusivity is going to show how easily heat flows through something, how easily heat flows through a material, and our thermal conductivity here, which is used in the thermal diffusivity ratio, is how easily heat or not heat, how easily temperature changes. In a material / situation. So that's really the short of it. That's my best explanation, is that without thermal conductivity, you couldn't have thermal diffusivity. Looking at this here, let's do a whole review and then we'll talk about it. So explain Fourier's law. Here's Fourier's law, where we have heat flux is equal to the thermal conductivity, negative thermal conductivity times the temperature gradient. And then we went through them step by step, talking about heat flux is watts per meter squared. Thermal conductivity is watts per meter Kelvin, and the temperature gradient is Kelvin per meter. And we stepped through what each means, kind of. Oh, and the negative sign, the important part. The negative sign just shows how Fourier's law flows from high temperatures to low. So we'll go high, start at high and go down. And this is important as in the law to make sure that we are following real life scenarios and that it can be used in day-to-day calculations. And then finally, this last part, what is the difference between thermal conductivity and thermal diffusivity? Thermal conductivity is used as a value to find thermal diffusivity. It's used in this ratio in the numerator up here. And alpha, our thermal diffusivity, is how easily heat flows through a material, while our K, which is our thermal conductivity, is how easily a temperature changes in a material, and is more about that value rather than our heat. So thermal diffusivity, I would say this is more about temperature, and thermal diffusivity is more about energy. I think that's a good explanation. So, yep, that's it.